You guys should now have an idea of what the different layers of the sun are, as well as a little bit about what's happening in each one. Today we're going to focus a little bit on what's happening on the surface, and then we're going to look at what's happening in the core. On the surface, the photosphere, what is going on? There are a few different things that happen that you're going to need to know about. A prominence, a flare, a granule, a sunspot, a spicule, and a CME, a coronal mass ejection. What I want you to do is take a look at this picture, and I want you to hypothesize what you think each one of these words means. Now that you've got your hypotheses, let's figure out what these are. We're just going to go in order. A solar prominence is any large, bright part of the sun extending outwards. So a prominence is something that is extending outwards from the surface. There you go. That's pretty simple. I want you to notice too that this, while it looks small on the sun, is actually extending out hundreds of thousands of miles. Planet Earth could fit many times over underneath this little loop. What is this solar flare? It's a brief eruption of very high energy. The sun's already putting out a lot of energy all over its surface. And if all of a sudden a bunch of extra energy comes out, we're going to see that as a solar flare. It's almost always outside of the visible spectrum. It's almost always outside of the visible spectrum, usually in ultraviolet or X-rays, even gamma rays. They're often associated with sunspots, which we will get to in a second. And these solar flares, if they are aimed towards planet Earth, can actually knock out communication satellites, which would then cause your phones and internet to stop working. Basically, teenagers everywhere go into meltdown mode. The next word that we need to know is a granule. So a granule, when I say that word, you might think of a granule of salt or a granule of sugar. It's a little tiny piece of something. A granule on the sun, if you look closely at the surface, the sun's surface has all of these little tiny granules. You can see that there's one. They look very, very, very tiny. Every one of them is bigger than the state of Texas. These are not little tiny features compared to humans. They're tiny compared to the sun. Every one of those granules is the top of almost like an elevator. So in the convective layer, which is just underneath the surface, convection means that you are taking material and you are moving it upwards because it's hot. Well, it's very hot in the center of the sun, so it's hotter down below, and that material is actually going to rise up through convection, almost like it's riding in an elevator. It's going to rise up to the surface, and you have millions and millions of these little tiny convective cells that rise up, and there's another one next to it, and another one next to it, and the tops of those convective cells are what we see as these little tiny granulations. So this would be the top of a little convective cell. This is the top of a little convective cell. And you might ask, why do they have these little darker lines in between them? What happens is that as that convective cell moves up and moves material to the surface, once it gets to the surface, it's going to cool down. And when that material cools down, it's going to move out of the way of the new material coming up, cools down and sinks. New material, hot material from the center rises up in that convective cell, gets to the surface, cools down, and then sinks. This in the middle is hot material that has just come to the surface, and this darker area around it, that's going to be cooler material that is now sinking back down into the sun. What then is a sunspot? Well, you'll notice that you have these little granules, and you have this giant dark area. And that giant dark area is when the magnetic field gets so twisted that it turns convection off. You don't have hot material rising up. Whatever's at the surface is going to cool down, and it's not going to be replaced by anything coming up. As it cools down, it's going to get darker in color, and then it's going to cool some more and get even darker, and cool some more and get even darker. When I say cooler, that's relative. It's still about 3,000 degrees Kelvin. The surface of the sun is about 5,800 degrees Kelvin. So it's about half as hot. Just as a comparison, 3,000 degrees Kelvin is about 5,000 degrees Fahrenheit. So it's cooler compared to the rest of the surface of the sun, but you don't want to land a spaceship there. I just gave you a preview of what we're going to talk about in a few days, how sunspots happen. But I also want you to know that these are huge, a couple thousand kilometers across. So these are not small objects at all. And they happen in an 11-year cycle. There's that 11 years coming back again. Every 11 years, you get a ton of sunspots. And then they kind of go away. So about 5 years after that, you get very little. And 5, 6 years after that, you get a bunch again. So you have this, a whole bunch of sunspots, not a bunch. A whole bunch, not a bunch. Remember what else happened in an 11-year cycle? The magnetic field flipped. Coincidence? I think not. The next word is a spicule. These are like, the sun has a flamethrower. It basically shoots a jet of superheated plasma straight out into space. This flamethrower shoots superheated plasma out at about 40,000 miles an hour. They get about 6,000, 7,000 miles out into space. So these are huge, huge gas jets being shot out from the surface of the sun. Where does that material go? Most of it turns into the solar wind, which we're going to get to later. Next one, a CME, a coronal mass ejection. This is the sun ejecting mass into the corona. Let me repeat that. Ejecting mass into the corona. Solar mass ejection. It's basically a huge sun burp. So instead of that little flamethrower jet, it's a huge, huge amount of material just being burped out into space. A little bit of reference, here's planet Earth. This is a CME. Many hundreds of times the mass of our entire planet just burped out into space all at once. If this CME got trapped in a magnetic field, where you have a North Pole and a South Pole, this would actually kind of bend back on itself. Then we would call that a solar prominence, because it's a little feature of the sun that's just shooting out from the sun and coming back. But because it's just being burped out into space, becoming part of the solar wind, this is what's known as a CME. Now, if this burps out a bunch of material into space and it's headed towards Earth, you get a whole bunch of ionized particles traveling towards Earth. And when those particles hit our magnetosphere, they start to glow. If you've ever heard of the aurora borealis or the aurora australis, the ones in the southern hemisphere, it's when the sky starts to glow up towards the North Pole and South Pole. And last but not least, wasn't on the photo, but the magnetosphere of the sun. You have a whole bunch of electromagnetically charged plasma that's being moved around in those convection cells inside of the convective area of the sun, convective layer. All of that charged material is going to create a magnetic field. And because they are all in different places, going different speeds, that magnetic field is going to eventually get very messy. Those convection cells, as the sun is rotating, are going to move. Some are going to move faster than others, depending on if they're towards the equator or the poles of the sun. You have a lot of magnetic field lines shooting out of the sun, and it looks like somebody has tied them into a knot. Eventually, those field lines will get more tangled until they snap back into place, and you have the sun's poles being flipped north to south, south to north. Here's a fun story for you. Back in 2012, 8 years ago, there was a CME, a solar storm. The sun burped out a whole bunch of ionized particles, and it was headed straight towards Earth. Now, if a whole bunch of those ionized particles all hit Earth at the same time, all of those particles are going to start bouncing around inside of our atmosphere. When they start bouncing around inside of our atmosphere, they are going to disrupt things like communication and power grids. Communication uses radio waves, which is a type of electromagnetic radiation. Power grid is moving around electrons, electricity, part of electromagnetic radiation. And if all of a sudden we get this huge influx of ionized particles, it's going to turn off communication and turn off electricity. It's going to be almost like an EMP, an electromagnetic pulse. If you've ever played a video game where they have one of those, an EMP fries the circuit boards. It overpowers the circuit boards and it fries them so that you can never turn them back on ever. If this had hit us head on, every single piece of electronics that was on that side of the Earth would have been fried and turned off forever. I want you to think about that. Cars, trucks, planes, all would have just been turned off. If you're in a plane, you're dead. If you're in a car going 50 miles an hour, you don't have brakes anymore because they're controlled with a circuit board. If you're on life support in a hospital, you're going to die. If you rely on a grocery store for your food, well, no trucks mean no deliveries. You're not going to have any food to eat. It would take our civilization, which is 100% dependent on computers and electricity right now, it would take it back hundreds of years. The problem is that hundreds of years ago, people knew how to farm for themselves. People could make their own tools. People could do a lot of things to keep them alive. Today, very few people know how to grow their own food, know how to do their own medicine, know how to make their own clothes. There would be worldwide famine. It would basically take Earth back to the Stone Age. The hard part is that it would only happen on one side of the Earth. Whatever side of the Earth was facing the sun when that EMP hit, when that CME full of charged particles hit Earth. If you're on the other side of the Earth, you're just fine. You're going to wake up in the morning and hear a bunch of news stories about how half of the Earth is now without electricity for good, and they're all fighting over food and medicine. There's been, car crashes and plane crashes and hospitals turned off in the middle of surgeries. Then the other half of the world is going to have to try to send food or aid or medicine or doctors or engineers to the side of the Earth with no electricity. It would basically destroy the economics of planet Earth. Luckily, that didn't happen. Otherwise, I have a very good feeling that most of us wouldn't be here right now. Because while it would not have destroyed the planet, it would have turned off an entire half of the planet's electronics, and we are very dependent on that right now. No computers, no vehicles, no communication, no medicine. It would have been bad. There's something fun to think about.